The lecture today is called Simultaneous Uniformization, column Dreams of Persistence. Uniformization of dreams is one of the main topics of the mathematics of the end of 19th century. During his whole life, Poincaré was proving this theorem, and he succeeded at the end. And I will tell you many things about uniformization. And after these things are all proved, all classical. After this, I will tell you some things about persistence which are dreams. I will tell you some conditional theorem, a theorem about simultaneous uniformization, which is not proved, and one persistence theorem that might be a consequence of that one. So the most part of this lecture is a definitely proved material, and another part is a dream. So first of all, I will recall you Riemann mapping theorem. If you have a topological disk in C, then there exists a conformal map H of this topological disk to a regular disk. This is a theorem from the general course of complex analysis. Students may know it. This theorem has a sort of dramatic history that is Riemann wrote a proof of this theorem, but this proof contained a guess and a gap, and this gap was filled by his successors. Now, there is a more tricky uniformization theorem. Consider an abstract, simply connected Riemann surface. Students, please raise your hands who knows what does it mean. Almost nobody. Wow. Well, and what is two-dimensional manifold? Please raise your hands. Not too many. So for those who raised the hand, I will say that the Riemann surface is a two-dimensional manifold with the charts that have a not only diffeomorphic but by holomorphic transition functions. So for those who did not raise hands, I will say more. Any of this surface may be covered by a neighborhood, and a one-to-one map of this neighborhood to the unit disk in C. Another point has another neighborhood which intersects U, it is V, and you have the same map HV. And this intersection is mapped in two ways. First of all, brings it here. And this map brings it here. So the transition function is defined as follows. Here, along this map, you come here, force this map, and you get a function of a complex variables with complex source and complex target. This is the transition function, and it is required that this is a conformal mapping, so holomorphic with its inverse. So this is a definition of a complex Riemann surface. So we take any abstract simply connected Riemann surface, and it is similar in a sense to a domain in the plane C. The question is, does there exist a conformal map onto something into the Riemann sphere? This is the Riemann sphere, C hat. This is the infinity point. If you delete the infinity point, you get the complex line C. And exists, the uniformization theorem says that for any simply connected Riemann surface, there exists a conformal mapping into or onto the Riemann sphere. Look that here we see at least two examples of a simply connected Riemann surface. The first one is the Riemann sphere itself. The Riemann sphere cannot be covered by one chart. There are two charts, one disk centered at infinity and another disk centered at 0. If you take in C the coordinate Z, then you may take a chart in the lower disk centered at 0 to be Z, and in the upper chart centered at infinity to be 1 over Z. And there are two charts in the intersection, and the transition function Z to 1 over Z is biholomorphic in this annulus. So, comment to this theorem. Your conformal mapping into the Riemann surface, a mapping onto, so I made no notation for this mapping, it is H. Let us put it there. H is onto, then the Riemann surface is itself the Riemann sphere. You may introduce a chart on it, an atlas on it, as I have shown. And this is called the elliptic case. H of our Riemann surface is C, then Riemann surface is also C and called parabolic. And if H of Riemann surface is a strict subset of C, then is hyperbolic. But there are many Riemann surfaces in analysis, not only simply connected. Why simply connected Riemann surfaces are so good? Because there is a construction called a universal cover. So let S be a Riemann surface that is, as I explained, a two-dimensional manifold or something like this. We do not know whether the non-contractible cycles on it or not. One has non-contractible cycles. And a universal cover occurs. Again, students, please, who knows what the universal cover is? One hand, two. Not too much. Then I will give the definition. We take a base point, an arbitrary one. And a point of the universal cover is not simply a point of S, but rather a path that connects the base point with S. This is an excessive set of points. If different paths are different points, then nothing good will happen. We identify two paths that may be contracted one into another along the surface S. So these are same points of the universal cover. But if the path cannot be contracted one into another, then these are different points. Yellow and pink are different points of the universal cover. So the universal cover is again a Riemann surface. A neighborhood of this point is just this set of paths. We take a neighborhood of the endpoint in S and extend the paths to all the points of this neighborhood. So this is the definition of the universal cover. Here is the definition, and I do not write it in words. And a very simple exercise is S hat is a Riemann surface again. So you have an atlas of charts on S. You can lift it to S hat. S hat is connected. And what is very important, that there are so-called deck transformations on the universal cover. Namely, you can take all the points of the universal cover. You can take more complicated yellow paths. I do not plot them. And then you add to all these paths so now then you get this curve. Every closed curve on S defines a so-called deck transformation of the universal cover. Suppose that this is just the picture for the universal cover. And here is the base point on the universal cover. It corresponds to a trivial point-wise path from this point to itself. And suppose that this point on the universal cover corresponds to this closed path. So the deck transformation will bring, if this path is gamma, the deck transformation is H gamma, and this is a conformal mapping of the universal cover to itself that brings the base point to the point corresponding to gamma. So, for those who never heard these definitions before, it is a serious material. It makes sense to make a pause here and to give you a chance to ask questions. So, once again, I defined Riemann surfaces, one-dimensional complex manifolds. I defined the universal cover, and I defined the uniformization mapping for simply connected Riemann surfaces. Now universal covers are simply connected Riemann surfaces, and by the previous uniformization theorem, they admit the conformal mapping to the Riemann sphere or the complex plane C or the unit disk D, elliptic, parabolic, and hyperbolic cases. And I defined important transformation. This is what I have done up to now. Now, just a verbal comment. I will not write anything on the blackboard. I will turn back to this when I will discuss Kleinian groups in the next lecture on Monday. So you have, once again, who knows what is the fundamental group? By one of S. Please raise your hands. Not many hands. Well, I will turn to this on Monday. Right now, I should say that this is a group formed by the loops in the Riemann surface. So the fundamental group, you may think about it now, right, as about a set of loops in the Riemann surface. Generates deck transformations as I have explained. If you take an arbitrary Riemann surface S, consider its universal cover, map it to the unit disk, this is the most often case, and consider deck transformations, then you have a lot of information about the Riemann surface itself. And it was a goal of Poincaré to get this information, and he got it at the end of his life. Once again, I will explain you what information occurs on Monday. Right now, I will stop by the definition of universal cover, uniformization, and deck transformations. Now I will switch to the situation that I want to discuss, to the situation which is a goal of the lecture today. Identical cycles. These are the complex cycles whose complex Poincaré map is identity. So you have a cycle on the Riemann surface, and nearby you have other Riemann surfaces with a cycle. And all this picture occurs when you consider a polynomial differential equation in the complex plane. This situation may be generated by a real differential equation. You can have a point with all the phase curves nearby closed. It is called, since Poincaré, a center. And you can complexify this picture and except for a singular point that I did not plot here, you will have this picture in C squared. So I think probably that I did not give you a general definition of the complex Poincaré map. Did I or not? No, I will do it now. You take a complex cross-section to the solutions. You take one complex cycle, one closed curve on the Riemann surface, and you take nearby points on the cross-section and continue the solution close to this cycle. Then you may prove that this continuation will bring to a well-defined point with the cross-section. This map is a map and therefore it will be biholomorphic, a locally defined biholomorphic map. In my example, it is identity. If the map is identity, then there are other complex cycles nearby, And they are called all identical cycles. If the Poincaré map is not identity, you have a cycle on the Riemann surface, you take a cross section, and you get a map which is not identity. It is biholomorphic. It is a one-dimensional biholomorphic map. It may have either identical fixed point, it is either identity, or has isolated fixed points. So if this fixed point is isolated, then this is a complex limit cycle. So do the identical cycles of a polynomial vector field, polynomial vector field in C square persist under with respect to the initial condition. So I change the initial condition. When I slightly change it, not leaving the neighborhood of the initial condition where the Poincaré map is defined, definitely I preserve the identical cycle. But then I quit this neighborhood, and I do not know whether the Poincaré map may be extended along the cycle or not. And that the answer is yes, probably we extend it not along the original curve in the cross section, but along a curve slightly changed, epsilon close to the original one. And this conjecture is one of the subjects of the lecture to follow, but I now pass to simultaneous uniformization, which is the main tool to attack this conjecture. So now I pass to the simultaneous uniformization, but before I write anything on the blackboard, I will illustrate simultaneous uniformization on this very picture. We take a cross section. It might be a rectangle, it might be a disk. And you take a point on this cross section. A complex phase curve, a complex solution of this differential equation passing through this point. And this is the Riemann surface. And we apply to it what was said before. Namely, we take its universal cover and we uniformize it making use of this theorem, of this uniformization theorem. Then you get something classical, something which is not at all questionable. But after that, you change the initial condition. And you take the uniformization of a nearby solution. Very good, no obstacle. Now the question comes, how this uniformization map depends on the initial condition. The dream is that it depends holomorphically. And this this uniformization, holomorphically depending on the initial condition, is called uniformization. So this is what the next section is about. So the next section is simultaneous uniformization. And now I give you some strict definitions. The union of the, consider the equation z dot equal to p of z. Consider a cross section B to the leaves. This is the transversal disk now. And let phi b be the Riemann surface, the leaf of the foliation passing through the point B. We define M. This is just a domain in C2 to be the union of all phi b. What is important, we take M hat to be the union of all the universal covers over phi b. And by definition, a simultaneous uniformization of the set of phi b, B is in B, is a biholomorphic map H of M hat into the Cartesian product of B times C such that the universal cover over phi B comes to so-called psi B. This is a domain in this the Cartesian product. This is B, this is C. If you take a point B here and take C that is over, then this is B times C. So psi B depends on B. Is a topological disk. And that's it. Any universal cover is mapped onto some topological disk, so is uniformized, and the map holomorphically depends on B because biholomorphic on universal cover. So I will not I will write you the main idea of what will follow. If a good, I did not define what this means good, simultaneous uniformization exists, then persistence of identical cycles holds. And now I will approach to what I mean by good. And in order it will make sense, I will communicate you Kirby distortion theorems. Good simultaneous uniformization should exist for a given global transversal section. That is, this disk is not necessarily small, probably a large one, transversal to leaves. You can take this section as a separate one. It is a valuable part of the one-dimensional complex analysis, usually not included in general courses, but usually not included in general courses, but very useful and very interesting. It deals with conformal maps again, with the biholomorphic maps, but now you are in one variable and there are no differential equations. And F is a conformal mapping of the unit disk inside the complex plane. Zero not necessarily comes to zero. The only requirement is that the magnitude of the derivative at zero equals 1. Then F has wonderful properties. F of D contains a disk of radius 1/4 centered at F of 0. So you come too close to the boundary of the image. The image contains the 1/4 disk here. For any R, the magnitude of the derivative is smaller than some function of R. It is explicitly written, but I do not do that. And same for the magnitude of F of Z itself, another function that I do not write explicitly. Better to say, probably I should better say that F of 0 is 0 because it is just a shift in the target plane, but I did not do that, so same for this difference. So these are valuable, excellent theorems. They have nothing to do with all the previous material. I should say that they look like a miracle because it seems, because the map F is arbitrary. So you take an arbitrary function of a complex variable with a minor restriction that it gives a bijective holomorphic map. And this restriction implies all these miracles. let me discuss good simultaneous uniformization Suppose that good simultaneous uniformization is abbreviated like this, exists. That is, look at the definition of the simultaneous uniformization. Here are the domains psi b that depend on b, the first requirement is that psi b are continuous in B. That is, if I take psi b and an arbitrary compact set inside, then for sufficiently close other b's, it will belong to the nearby psi b. Psi b a union of psi b's, or better to say, any psi b has the following property. A disk of radius r small for some r belongs to psi b, and a disk of some large psi b. So this is good simultaneous uniformization. Now, have a cycle on the phase curve phi b. The identical cycle on phi b. For b in a subset of b. So we have the following situation. This is b, this is d, and for any point in D, the Riemann surface phi b has a disk. Then there is a deck transformation, as I explained, corresponding to this disk of psi b onto itself. The theorem says that if phi b has a cycle gamma b for b in the disk D is open, then phi b has a cycle gamma b for almost every b on the boundary of our disk D. An identical cycle exists on one solution, then it exists for all nearby solutions. So we can extend the identical cycle at least across the boundary of the disk. And the kernel of the proof of this theorem is the following. We have the deck transformation say GB of psi b to itself for B in D. Then for almost every B in the boundary B0, there exists, let me say, and a sequence of points in the disk converging to this B0 on the boundary, exists a limit of the desk transformations corresponding to Bn equal to G B0. It will be a conformal map of psi B0 onto itself. And if we have this conformal map, then it is a deck transformation for some cycle, and this cycle is the extension of the identical cycle to this point B0. And the existence of this limit may be rather easily deduced from the Köbe distortion theorems that I stated. And this is the very sketchy picture of the relation between simultaneous uniformization and persistence. So I gave you a widely dashed of the transition from simultaneous uniformization to persistence. It is very much dashed because it is addressed to people who hear for the first time these fundamental notions from complex analysis and topology. But I hope that you have at least some highlights on this path, and that the information that I communicated to you, which is independent on the persistence problems and simultaneous uniformization, will be still useful for you. Thank you.
Well, is there any question?
I'm ready to answer questions.
So you said there was a dream attached to all this. I guess that's the part 7. How often do you expect good uniformization to arrive?
I have some approach to simultaneous uniformization that was not tried before, but I did not yet seriously tried being involved in.
But do you expect it to happen generically? Some sense?
Well, I will speak in the next lectures. I will speak about simultaneization of foliations by algebraic curves. And this is a deeply developed theory by Birds and Alfors. The very term simultaneous uniformization comes from Birds. So there are completely non-trivial theorems about simultaneous uniformization. I recently proved a theorem about simultaneous uniformization of algebraic curves with variable topology, which is not included in the Birds theory. So this is what I wanted to explain in the next 2 lectures next week.
Okay, thank you.
Any other question?
This David distortion reminds me of Schwartz lemma. Is it related to Schwartz lemma?
No, they are not based on the Schwartz lemma. They are based on a so-called area distortion theorem. So they are included in textbooks, and the proof is not so long, 1 or 2 pages.
Not in Alfors, no.
I don't remember. I think that in Courant they are present.
Thank you.
We have also people that are connected. If some of the audience who is connected has a question or some commentary, they can talk. Please feel free to talk.
So, and I am open to questions after the lecture for some time.
No one? No one that of those that are online? No, it seems not. And here, do we have more questions?
just an acceleration. The H mapping you commented there is the conformal map that we got from the uniformization theorem, right? So you can classify the Riemann surface in those three cases through the conformal mapping. That's what you're doing there, right?
Yes, here is the general uniformization theorem. The uniformization map is here defined by F. Sorry. I did not write the notation for this uniformization mapping. What is the question?
I just asked if that classification of the Riemann surface was through the mapping that the general uniformization theorem offers us.
Yes,
Yes.
exactly.
Yeah,
Exactly.
thank you very much.
I did not say the classification of Riemann surfaces which are not simply connected. We take a Riemann surface, we take a universal cover over it, and the Riemann surface is of the same class as the universal cover, elliptic, parabolic, and hyperbolic.
Thanks.
Can you please repeat who is phi in that second part of the Covey's distortion theorems?
What do you ask about Kobe distortion theorem?
Who is what is the function phi?
So this is the pure Kobe distortion theorem, and it should be applied to the deck transformation GB corresponding to an identical cycle on the leaf phi B passing through B in the good disk D. Is this your question?
My question is
No, I did not at all explain you the transition from this limit, from Kobe distortion theorems to this limit process. I only said that you can prove the existence of this limit with the use of the Kobe distortion theorem and the assumptions that the simultaneous uniformization is good. So this family of domains behaves in a sense well. They are continuous with respect to the point and it's a disk and is contained in a disk. And the disks are the same for all B's.
okay. Thank you.
Just out of curiosity, in Covey's distortion theorem statement, we mentioned a function phi depending on R. What is that phi function? Is it holomorphic? Is it analytic?
Well, you have a domain psi. What function do you discuss?
Above on the statement of Covey's distortion theorem.
Let me see. Kobe distortion theorem, second part. I see. This function phi. This function phi is, as far as I remember, it is the derivative of the function like this.
Okay. Thank you.
As far as I remember.
Thanks.
More questions? No? If not, let's thank the speaker, Yulij Sergeevich.